Mr. Boer here with our second part of our sound and light. The last video segment, we talked about waves in general, and the characteristics that all waves have, whether they're sound or light, and the two main types of waves, one being longitudinal, the other being transverse. We're going to look at longitudinal wave, and probably the most famous of those waves that we talk about is sound that you have in chapter 26 of your book. I mean, why is sound important? Because obviously it's something we hear. It's what we use, hopefully, to understand things. It's a way of communication. So we have both sound and light being a important part of life itself. So if we look at the origin of sound, again, all waves come from some type of vibration. So that vibration can come from a string, like a stringed instrument. As you pluck it, it produces a vibration and a sound. It can come from a reed that we would find in one of these band instruments, like a saxophone or a clarinet, or it can come just from your vocal cords. As air passes through those vocal cords, they vibrate, and that vibration produces a sound, which could come from a flute or something. But all waves come from a vibration. In this case, the vibration is the string, the reed vibrating as you pass air through it, or the vocal cords itself. Again, if we kind of review what a longitudinal or sound wave is, it's a compression. So what you're doing is you're taking those air molecules, you're compressing them together, and then they're refracting. Compression, refraction, which when you look at a wave still would end up having your crest where all the particles are together, your trough when they're the farthest apart, still has those same, you'd end up having a wavelength and amplitude and a frequency. So all waves end up having that, even sound. The frequency is what we perceive as pitch. So those of you that are more musically inclined than I am know that there's different instruments produce different pitches that you would have. A person normally, we say, has a hearing range anywhere from 20 to 20,000 hertz. Now that does depend. Not every human's exactly the same. That's why it's a range. As you get older, it starts to break down, and that hearing range actually shrinks. So when you say older people, like me, I guess, can't hear as well, that's true. We don't have the same hearing as younger people. And animals have different hearing ranges too. Anything that's below that 20 hertz is going to be called infrasonic, which we would use to monitor earthquakes and things like that. And obviously not audible that we could hear it. Anything higher than that's called ultrasonic, anything higher than 20,000 hertz, the audible range that we have. And then we would use those for ultrasounds to see babies and all the fun stuff that you could use for those. But it's a compression and refraction is how sound is produced. It's going to travel in all directions, this compression and refraction. But basically, you get the two fields that take place. You're still going to have that wavelength. You're going to have a crest and a trough that ends up making this work. What you have to know, though, with sound is you have to have something to compress in order for sound to travel. So sound, we say, needs a medium to travel through. It needs a solid, a liquid, or a gas. It needs something. It does not travel through empty space because there are no particles. In a vacuum, sound does not travel. It needs a medium to travel through. So in general, sound is transmitted faster in liquids than in gases, and they would be faster in solids than in liquids. So the more particles and the closer those are, the density of those obviously can change the speed of how fast they're being contracted. You know that sound cannot travel in a vacuum. It needs something to be compressed. If we look at the speed of sound, now it's going to change because air, as we said, the speed of sound in dry air is different than wet air because of the number of molecules. But on average, we say about 330 meters per second, which we would give that term like a Mach. If you've ever heard all planes travel 3 Mach, that's dealing with, in comparison to the speed of sound in air, about roughly 330 meters per second. That changes based on elevation, based on humidity, but we're going to give it an average. The speed is dependent upon its elasticity, not necessarily its density. I know it's easier to think about density, but really it is elasticity which determines the speed. As long as that molecule can be compressed and then put back to its original shape easily, it's going to travel faster. Like through steel, those steel pipe,